Hello everyone, once again welcome to our physics class. Hope you all are fine over there. Children, in our previous chapters, that is in chapter 8 and 9, we have learned about motion and also force as a cause of this motion. We learned that a force is required to bring about an acceleration. We had observed whenever an object is dropped from a certain height, it will fall towards the earth, towards the ground. Also, we can see the planets move around the sun. Moon goes around the earth. In all these cases, some force is responsible that acts on the motion of these objects, planets and the moon. Isaac Newton could grasp same force is responsible for all this phenomena. And that force is called the gravitational force. So today we shall discuss about gravitation and gravitational law, universal law of gravitation. Also we will discuss the motion of objects under the influence of gravitational force. So let's get started with today's session. Children, as discussed in our introductory video, let's discuss about the gravitation. We know that the moon goes round the earth. An object when thrown upwards reaches a certain height, then falls downwards. It is said that when Newton was sitting under a tree, an apple fell on him. The fall of the apple made Newton start thinking. He thought that if the earth can attract an apple, can it not attract the moon? Okay. If earth can attract an apple, why not moon or other celestial bodies? If moon is attracted by the earth, why it does not fall towards it? Isn't it? Why moon is not falling towards the earth? And why earth is not moving towards the apple? These are some questions which came to Newton when he saw an apple falling from a tree. Okay. And he conjured that the nature of force is same whether it is moon or earth, and earth attracts all bodies. Now, as force is there, then why there is no acceleration? So it is well understood that there is some force by which the earth attracts all the bodies. So now, as force is there, then why there is no acceleration? Well, there is acceleration. It is called centripetal acceleration, and the force which causes this is termed as centripetal force, which acts towards the center. You know, Earth revolves around the sun. Not only Earth, all the planets revolve around the sun in a circular orbit. So they maintain that circular path. And whenever an object is moving in a circular path, the object experiences a centripetal acceleration and also a centripetal force towards the center of that circular path. Okay, and this centripetal acceleration helps to maintain the planets or the earth to move in a circular path. Now, an object moving in a circle experiences a centripetal force. It changes the direction of object at every moment. In the first chapter, that means chapter 8 motion, we had discussed about the circular motion, and there we had studied that whenever an object is moving in a circular path, it changes its direction at every moment. That's why we consider uniform circular motion as an accelerated motion. So that is what is said here. An object moving in a circle experiences a centripetal force due to which it changes the direction of the object at every moment. These 2 points can explain the movement of planets around the sun. The motion of moon around the earth is due to centripetal force. The centripetal force is provided by the force of attraction between the earth and the moon. Okay, so there must be some other force required to balance the centripetal force. Otherwise, if centripetal force dominate, then what happens? The objects may fly off from their circular path, and it may have a tendency to fall into the center of that circle. It must not happen. So there must be some other force to balance this centripetal force. In the case of motion of moon around the earth, the centripetal force is balanced by the force of attraction between the earth and the moon. Now, the earth is also attracted towards the apple by the same amount of force in accordance with the Newton's third law. Okay, see, if earth attracts apple towards it, then apple also attracts earth towards it as per Newton's third law, because according to Newton's third law, for every action there is equal and opposite reaction. Okay, so if earth attracts apple, then apple must also attract the earth with the same amount of force. But we cannot see apple moving because acceleration is proportional to the mass, and mass of the earth is very large in comparison to apple, isn't it? See, we can see from the second law of motion, we know that F is equal to ma, and from this A is equal to F by m. So acceleration is inversely proportional to mass. So for massive objects, acceleration will be very small, and for less massive objects, for lighter objects, acceleration produced will be very high. So compared to apple, earth is a massive object, so it experiences a very less amount of acceleration. On the other hand, apple experiences a large amount of acceleration due to its small mass. So that's why we see apple falling towards the earth. At the same time, the earth does not fall, or earth is not attracted towards that apple. Earth is, even though attraction is there, the earth is not moving towards the apple because of its large mass. Okay, so that is said here. The earth is also attracted towards the apple by the same amount of force in accordance with the Newton's third law, but we cannot see it moving because acceleration is proportional to mass, and mass of earth is very large in comparison to apple. Okay. So we do not see earth moving towards the apple. Now extend the same argument for why the earth does not move towards the moon. In our solar system, all the planets go around the sun. By arguing the same way, we can say that there exists a force between the sun and the planets. From the above facts, Newton concluded that not only the earth attracts an apple and the moon, but all objects in the universe attract each other. This force of attraction between objects is called the gravitational force. So according to Newton, every object in the universe attracts every other object with a force. And this force of attraction that exists between the objects in the universe is called gravitational force. And he has also formulated a law based on gravitation, and which is his famous universal law of gravitation. So next, let's discuss and state the universal law of gravitation. Universal law of gravitation. So the Newton's universal law of gravitation states that every object in the universe attracts every other object with a force which is directly proportional to the product of their masses and inversely proportional to the square of distance between them. Okay, so every object in the universe attracts every other object with a force, and this force is our gravitational force. What is the nature of that force? That force is directly proportional to product of their masses and inversely proportional to square of distance between them. This gravitational force is a universal force as it applies to all bodies in the universe, and this law of gravitation is a universal law as it is applicable everywhere in the universe. And this gravitational force acts along the line joining the centers of two objects. And let's try to frame the mathematical expression for this universal law of gravitation. Here you can see there are two objects. m1 is the mass of one object, m2 is the mass of another object. D is the distance between the centers of the objects. So while calculating gravitational force, we must be very careful. We must consider the distance between the centers of that objects as shown in the figure. Now, as per Newton's gravitational law, this object with mass m1 attracts another object of mass m2 with a force, that is F. And as per Newton's third law, if one object exerts force on another object, then the second object will also exert a reaction force on first object. So this F is the reaction force. So m1 attracts m2, similarly m2 also attracts m1 with a force. Okay, now what is gravitational force? What is the expression for gravitational force? See, as per law, gravitational force is directly proportional to product of their masses. So m1 into m2 is the product of the masses, and also gravitational force is inversely proportional to square of distance between them. So what is the distance between the objects? D. Square of distance between them will be d square. Whenever you combine these two expressions, you will get F proportional to m1 m2 by d square, isn't it? And to remove the proportionality symbol, we will add a constant, and the constant here is capital G. Capital G into m1 m2 by d square. And when capital G is known as gravitational constant. Capital G is gravitational constant and its value is a constant, and you must remember this value. The value of capital G is 6.673 into 10 raised to minus 11 Newton meter square per kilogram square. It's very important to study the magnitude of capital G as well as unit of capital G. So what is the magnitude of capital G? It is 6.673 into 10 raised to minus 11. And what is the unit? It is Newton meter square per kilogram square. So that's about universal law of gravitation, and this expression is very, very important. Always remember this expression. So what is the expression for universal law of gravitation? That is F is equal to G m1 m2 by d square. Okay, and in some books you can see, in our NCERT book you can see the expression like this: capital G into capital M into small m by d square. So where capital M indicates mass of one object and small m indicates mass of another object. Okay children. Now, what is the importance of this universal law of gravitation? So the universal law of gravitation could successfully explain several phenomena which were believed to be unconnected in one time. So it could explain the following things: the force that binds us to the earth. Okay, which force binds us to the earth? That is the gravitational force, which was explained by universal law of gravitation. The motion of the moon around the earth, as we discussed in our introductory video. The motion of planets around the sun. The tides due to moon and the sun. Okay, all these natural phenomena were explained using the universal law of gravitation. So that is the importance of universal law of gravitation. Also the rainfall. It is explained using universal law of gravitation. Why raindrops are falling down? Why raindrops are not moving upwards? Okay, so such things were beautifully explained by the universal law of gravitation. Next, let's discuss about free fall. We have learnt that the earth attracts objects towards it. This is due to gravitational force. And whenever the objects fall towards the earth under the influence of gravitational force alone, we can say that the objects are in free fall. For example, consider there is a stone on the second floor of a building, and simply drop that stone. The stone falls to the ground. That motion of the stone will be a free fall, because in such type of motion only gravitational force acts. That is, the stone is falling down under the influence of gravitational force alone, if we neglect the resistance offered by the air. Okay, so the motion of an object under the influence of gravitational force alone is known as free fall. Okay, so when a body is under the influence of gravitational force of earth only, then we say that the body is under free fall. Practically, it is possible under vacuum only, as there is always some air resistance present. Okay, you know that in real situation, objects cannot fall under the influence of gravitational force alone, because some sort of resistive force offered by the air is also present. So whenever the object is falling downward, the resistive force of the air acts in the upward direction. But at the same time, if it is a vacuum means the absence of air. So whenever an object fall in any vacuum situation, there won't be any resistive force offered by air. So in such cases, the object falls under the influence of gravitational force alone. Only gravitational force acts on the object whenever it is in the vacuum. Okay, and you might have noticed, whenever the object falls down, there is a change in the velocity of the falling objects, isn't it? While falling, there is no change in the direction of motion of the objects. Object is still moving downward, so there is no change in the direction of motion. But due to the Earth's attraction, there will be a change in the magnitude of velocity. Okay, so any change in the velocity involves acceleration. Whenever an object falls towards the Earth, the velocity of the object increases. Whenever the velocity increases, there will be an acceleration, and this acceleration involved in free fall is known as acceleration due to gravity. This acceleration is due to the Earth's gravitational force. Therefore, this acceleration is called acceleration due to gravity, or acceleration due to the gravitational force of the Earth. And acceleration due to gravity is denoted by small g. So there is capital G and small g. Capital G is gravitational constant. Small g is acceleration due to gravity, and it is also a constant, and its value is 9.8 meter per second square. Acceleration due to gravity is a constant and its value is 9.8. Since it is acceleration, its unit will be meter per second square. Okay, so free fall of apple. Falling of apple is under the influence of gravity, so it can be regarded as a free fall. Okay, and the acceleration experienced by the object in a free fall is called acceleration due to gravity, and this acceleration is due to the gravitational force of the Earth. Now, value of G is found by this expression, small g equal to capital G into m by d square. Okay, so this is the expression to find the value of small g. Capital G into m by d square, where capital M is the mass of the earth and small d is the radius of the earth. Okay. Now we know that earth is not a perfect sphere. It is oblate. As the radius of earth increases from the poles to the equator, the value of g becomes greater at the poles than at the equator. Okay. Children, we know that earth is not... Children, listen here. On the screen you can see the structure of an earth. It is not a perfect sphere. It is oblate in shape. So this is the center of the earth. Let this be the center of the earth. And this is the polar region. This is the equatorial region of the earth. From the center to pole, let the radius be r1. From the center to equator, let the radius be r2. Anyway, since we consider earth as a sphere, r1 and r2 both form the radius of that earth itself. Okay. Now, at the polar region, how will you calculate small g? You know, this is the equation to calculate small g. Small g is equal to capital G into m by d square, where d is the radius of the earth. So in this case, we can rewrite the equation like this. Acceleration due to gravity small g equal to gm by r square, where r is the radius of the earth. So at the polar region, radius of the earth is r1. That means the distance from center to pole is r1. So small gp, the equation will be gm by r1 square. Now, what is acceleration due to gravity at the equatorial region? At the equatorial region, it will be g into m by r2 square, because the distance from center of the earth to equator is r2. Now, which is greater, r1 or r2? Yes, r2 is greater than r1, isn't it? So r2 is greater and r1 is less. So if the value in the denominator is less, then the fraction will be more. So if r1 is less, then acceleration due to gravity will be more. And if r2 is more, then acceleration due to gravity will be less. That means the acceleration due to gravity at poles experienced by an object at the polar region will be greater than the acceleration due to gravity experienced by an object at the equatorial region. Okay, and there will be only a very small variation. If acceleration due to gravity at the polar region is 9.8, then acceleration due to gravity at the equatorial region will be 9.75, like that. So there will be a very small variation between the acceleration due to values of acceleration due to gravity. Hence, we can consider this small g as constant itself. Even if there is a small variation, we can consider it as nearly a constant value, 9.8. Okay, but there is a slight difference in the value of acceleration due to gravity. And where is it more, where is it less? You must remember, the acceleration due to gravity is more at the polar region than at the equatorial region. The value of g becomes greater at the poles than at the equator. For most of the calculations, we can take small g to be more or less constant or near the earth. Okay, but for objects far from the earth, the acceleration due to gravity will be different. Okay, for example, the value of g, small g, in earth is different than the value of g in moon. Okay, children. So that's about acceleration due to gravity. Now, motion of objects under gravity. See, let's describe an activity. Take a sheet of paper and a stone. It's an activity in your NCERT textbook, activity 10.3. Okay. So let us take a sheet of paper, a stone, and also drop them simultaneously from the first floor of a building. Just observe whether both of them reach the ground simultaneously. See, what will you observe? We can see that the paper reaches the ground little later than the stone. This happens because of air resistance offered. The air offers resistance due to the friction to the motion of falling objects. The resistance offered by the air to the paper is more than the resistance offered to the stone. And if we do the same experiment in a glass jar from which air has been sucked out, that means if we do the same experiment in a vacuum, the paper and the stone would fall at the same rate, because in vacuum there is no air to offer the resistance to that paper or that another object, a stone. Okay, similarly, if we take different objects, let it be a pencil, pen, stone, then eraser, your rubber, scale, ruler, everything, just drop them simultaneously from the first floor of a building. You can see all the objects will reach the ground simultaneously. Okay, at the same time, if you take a crumpled paper and a plain sheet of paper, which of them will reach the ground first? Obviously, it will be a crumpled paper, because the air offers more resistance to the plain sheet of paper than the crumpled paper. Okay, so the acceleration experienced by the objects in a free fall will be same. It does not depend upon the mass of the objects. Okay, so the acceleration experienced by an object in a free fall is independent of its mass. This means that all objects, hollow or solid, big or small, should fall at the same rate. And there is a famous story of Galileo. Galileo dropped different objects from the top of the Leaning Tower of Pisa in Italy to prove the same. Okay, so Leaning Tower of Pisa in Italy to prove the same. As g is constant near the earth, all equations for the uniformly accelerated motion of the objects become valid with acceleration a replaced by g. Okay, so we can see here we take value of g, constant near earth. So equations for uniformly accelerated motions are applicable, and there we want to replace a with g. These are our equations of motion. Do you remember the three equations of motion? What are the three equations of motion? First is v is equal to u plus at. So here, for instead of a, you must substitute g, because it is a free fall. So equation will become v is equal to u plus gt. Second equation of motion is s is equal to ut plus half at square. Here also a is replaced by g. So it will become ut plus half gt square. Third equation of motion is v square equal to u square plus 2as. And here a is replaced by g. So the equation becomes v square equal to u square plus 2gs. Okay. And the most important point here is the sign convention. That is, this g has different sign for different directions of motion. Value of g is positive if acceleration is in the direction of velocity, and vice versa. That means if the object is falling down, value of g is taken as positive, and if the object is moving up, value of g is taken as negative, since the object is moving against the force of gravity when it is moving upward. Okay, so that is written here, value of g is positive if acceleration of the object is in the direction of velocity, and vice versa. Okay, children. So with this, I am concluding my session. Notes of the topic and YouTube video have been uploaded. Just go through it. We will meet in the next session. Till then, take care all of you. Stay home, stay safe. Thank you.